move on to the AC analysis. And then after that, you know what we're gonna have, right? We're gonna have exam number 2.
How many lectures do you think?
The AC is always longer, right? So I will
Three.
probably 3 to 4 lectures.
Another exam.
Yeah, then the exam. So if you look at the calendar, maybe toward the middle of November.
Okay.
Is it?
Yeah.
Or not? I guess. And then we have one more chapter to cover. Okay. And then we have the final exam. By the way, our exam is a little bit late this year. The final.
Okay.
It's on Wednesday of the exam week. But that's good. It means you have more time to study.
Yeah.
But if I were you, I would like to get it over sooner. But we cannot change the schedule. So
No.
school policy. Right? Okay. So. Alright, so VDD is 12 volts, R1 plus R2 equals to 100K. VPN is 1 volt, Kn is 1 milliamp per volt square. Alright, IDQ is given. It's 2 milliamp. Also, we know the Q point is located in the middle of equation. Okay. Alright, so that's all the information we have. So this is a design problem because some of the components in the circuits are not known. Okay? So I guess we have to find all the 3 resistors. Huh? We have to find R sub B, R sub 1, R sub 2. First of all, you have to understand the meaning of that. So let me draw the low line and the Q point. Okay? So this is always VDD, correct? And this is always VDD over RDC. And then there's a locus, right? And that is the P point, yes? So this is IDP, this is VDSP. As I mentioned last time, the P point represents the upper bound of the DC operation. Yeah? Okay. Now, if you look at this information, Q point is in the middle. That means what? Okay, that means IDQ is head of IDP. VDSQ. So VDSQ must equal to VDST plus half of VDD minus VDST. Correct? This must be that plus that, right? And this is half of it, half of the difference of this, right? Plus that, so that is VDSQ. Okay, if you understand this concept, you're halfway home. There's a commercial, because I fly a lot. There's a commercial, I forgot what's the airline. There's a guy boarding the plane, and then he was smiling. He said, "Oh, I'm halfway home." Not funny?
It's a frequent flyer joke. Can't afford it.
I don't travel too much this summer.
We appreciate that.
Okay. So, what do we start? Well, you can look at the, let's call this VG, right? And this is VGS. And this is ISOP, right? Okay. So you should know that VG is the same as VGS, right? And IDQ is equal to Kn VGSQ minus VTN to the square. I do not have to, this is the equation for saturation, right? I do not have to assume saturation because I know, by looking at this, I know that the MOSFET is in saturation, correct? If the Q point is located below the locus, that is saturation. So I know for sure that I'm in saturation. Okay, so therefore you can use this equation. Now, do I have one unknown? Yes. This is known, right? So this is 2 times 10 to the minus 3. Kn is given, right? Kn is 10 to the minus 3. VGSQ minus VTN is 1. Right? So you have one unknown. So you can calculate VGSQ, and that's equal to 2.4 volts. Okay, and as I said, VGSQ equal to VG, right? Look at the circuit. The VG is what? It's VDD based on the voltage divider rule. Yes? Okay, then again, I got one equation and one unknown. The unknown is this guy. Got it? Because R1 plus R2 is given. This is known, this is known, right? So therefore, I can find R2 equal to 20K. And once you know R2, you know R1, huh? So R1 is equal to 80K. All right. Now I have to try to find R sub B, and I have to go to the output loop. So you do the output loop equation, VDD equal to VDSQ plus IDQRD, right? again, you look at the equation to see how many unknowns you have. This is known, right? This is not known. That is not known. This is known. So you've got two equations, one equation and two unknowns. So you need one more equation. So hopefully I can try to find VDSQ, right? Okay. As I said earlier, VDSQ is equal to this equation, huh? So VDSQ equal to VDST plus half of the difference of PV and VDST, right? So in order to calculate VDSQ, I had to figure out the value of VDST, huh? Correct? So therefore, I need to calculate VDST. Okay, so now we're going to go to the formulas for calculating the T point. Okay, remember, there are three equations. The first equation is what? Is the output loop equation, but instead of Q, you have T, okay? So that's always the first equation. The same KVL for the output loop, but now you put T instead of Q. Okay, what's the second equation? You remember? IDT, because you are at the substitution point, so it's always the saturation, right? So it's Kn VDST squared. Okay, so now you put this in here, right? You get VDD VDST plus Kn VDST squared times cos T. See, now you have one equation and then one unknown, right? So, from this equation, from here, okay? From this equation, I can calculate VDST, and the number for that is 2 volts.
How'd you do that if you don't know RD?
Huh?
How'd you do that if you don't know RD?
Oh, wow. That's right. How do I know? How do I do that?
IBT is 2 times IQ.
Oh, yeah. Go back, okay? So actually this is known, correct? So this is known, so I need to go from here, right? From this equation, IDT is known. Is 2 times. Is 2 times IDQ, correct? Right here. Okay. So therefore, so IDT is 4, correct? 4 times 10 to the minus 3 equal to Kn VDST squared. Yes? And Kn is 10 to the minus 3 VDST squared. So therefore, VDST is plus or minus 2 volt. Now, of course, you don't use minus 2, right? So you use 2 volt, plus 2 volt. All right. So now this is known. So I don't think I need this equation, huh? Do I?
No,
I need that later, I think. Oh, it's right somewhere. Anyway. So now I go back to this equation. Yes. So VDSQ from this equation, right, is equal to 2 plus 12, yes? 12 minus 2 over 2. So VDSQ must be equal to 7 volts. Okay, then I put this up here, right? This equation. So VDD equal to VDSQ plus IDQ RDS. So therefore, I can find RD, that's equal to 2.5K. Right? Good question? Right. So now I'm going to do a different type of circuit. So this is a little bit like a case code, right? So you have one transistor on top of the other. And this has been used quite frequently. And you notice there's something unique. That is the one on the top has the gate and the drain connected together. And this is normally called the load. And this is called the driver. And actually, the load, typically when you have a load, it's a resistor, right? But in the MOSFET circuit, people would prefer to use this type of load. It's called active load. All right. Now we have to figure out what are the currents and what are the voltages, right? So this is the VGS load, right? This is the VGS driver, and this is the IB load, IB driver. But I think before I do this, maybe it's better I should first focus on this circuit, okay? So let me do that. So let me do this circuit first, which is a part of the circuit. All right. So this code is MOSFET. So this is VGS, right? This is VGS, and this is ICP. Of course, that's also ICP, right? All right. So we know R squares equal to 10 K ohm. BTN of the MOSFET is 0.8 volt. K sub n is equal to 0.05 linear parabolic square. So let's find I sub b and yes. Okay. Because the gate is connected to the drain, yes? So VDS is always equal to VGS, correct? Huh? VDS, VGS, right? They must be the same. Okay, then, you know, VD set is equal to VGS minus VTN, correct? That's the formula. This is the voltage that can cause the MOSFET to saturate, yes? Okay, then put this here, VD set equal to VDS minus VTN, right? We put this here. Then, from this equation, you know that VDS is always larger than VD set. Yes? From here. Because this is a positive value, right? So this must be larger than that. By how much? By VTN. Therefore, the conclusion is that every time when you have a MOSFET that has the gate tied to the drain, the device is always in what?
Saturation.
Yeah. Always in saturation. Okay. So that's the first finding. Well, if it's in saturation, then my formula for the drain current is what? Is Kn VGS minus VTN to the square, right? Which is the same as saying Kn VD set square. Yeah, last time I remember I discussed K7, right? K7 is equal to what? It's 2L omega mu 7 C oxide, correct? Something like that. Okay. Then, see, I told you that the trend for the advancement of the technology in the past 30 years has been what? Has been the scaling of MOSFET. And how do you do the scaling? If you look at this equation, it's very simple to see, okay? You reduce L, right? Becoming smaller. You increase mu7, right? You increase C oxide, yes? Because by doing that, you can try to increase K7. If you increase K7, you can increase what? Drain current. You want the drain current to be as large as possible. So that, in just a nutshell, that tells you what is going on in the past 30 years, okay, in the MOSFET technology. So people working in this area has always tried to do that. And, you know, L now becomes 10 nanometer, huh? 30 years ago, L was like 10 micron. That's how many times? How many orders? 3 orders, right? Difference. Okay. mu7 I talked about this a little bit last time. I told you that you can try to press the silicon, right? And I forgot a name for that. Now I remember. It's called strand technology. So if you read the literature, you see strand, S-T-R-A-I-N. That means you are trying to squeeze silicon, and that can end up with a higher mobility. And how do you increase C oxide? C oxide is equal to epsilon oxide over T oxide, correct? It's the dielectric constant of silicon dioxide. That is the thickness of the oxide layer. So how do you do that? Try to increase this, try to decrease that, correct? Currently, T oxide has been reduced to just a few angstrom. 5 angstrom. You know what's an angstrom? Angstrom is 10 to the minus 10 meter. So it's very, very thin. Now, if you try to increase that, you would have to use a different material, and that is called, I mentioned it last time, it's called high K. Okay? So I thought I'd give you this background. All right, so let's go back to the example. Do I know everything here? Huh? I know Kn, VGS. I don't know VGS. VGN is known, right? Correct? Okay, so I cannot solve it. I need a second equation. So now if I go to there's no equation for the input loop, right? Correct? Yeah, there's no input loop. There's only one loop, the output loop. So I can go to the output loop, VDD equal to VDS plus IDRS. Yes? And this is VGS plus IDRS. VDS, as I said in the beginning, VDS equal to VGS. Right? Okay, so now VGS from this equation become VDD minus IDRS. So let's call this equation 2. This is equation 1. Yes? Now I can put equation 2 into equation 1. Got it? So I get ID equal to Kn. VGS is here, right? VDD minus IDRS minus VDN on the square. Right? So this is the result of combining equation 2 and equation 1. Okay, now we have one unknown, right? ID. So this is equal to Kn, whatever Kn is. It's 0.05 times 10 to the minus 3. VDD is oh, no. Okay, so let's say VDD equal to 50. Okay, so 5 minus ID times R sub S, that's 10 to the 4, yes? Minus 0.8 to the square. So this is a, so let me combine all this. So it's 5 ID squared minus 5.2 ID plus 0.9.0. Okay? So from here to here, it's just like that. Yeah? So this is a quadratic equation. You're going to find two solutions. One solution is ID equal to 0.8 milliamp. The other solution is 0.2 milliamp. Oh, so both solutions look reasonable, right? So what do you do?
Plug them in.
If one is negative, you know what to do. Unfortunately, both are positive. So you have to try to find a way to figure out which one is the correct solution. So you have to put this back to somewhere. I think you have to put this back to here, okay? So you go to the output loop equation. Okay, so output loop equation, VDD equal to VDS plus IDRS, correct? Okay. So this is known, correct? 5 volt. RS is known. This, we have two solutions, right? 0.8 or 0.2 milliamp. Okay, so you use that to calculate your VDS. So VDS will be equal to minus 3 volt if I sub B equal to 0.8 milliamp, and will be equal to 3 volt if I sub B equal to 0.2 milliamp. Okay, so now you know which one you should have to use, huh? So you have to use this one, correct? So therefore, the solution is that I sub B is equal to 0.2 milliamp and VDS is equal to 3 volt. Now we're going to go back to here, all right? So that's a simpler problem than this one, right? Questions? Okay. Is that? So you can see that in this circuit now, we have two MOSFET. One is serving as the load, the other one is serving as the driver. Okay? Now I'd like to find out so I have to give you some problems, correct? Okay, so VDD again is equal to 5 volts. Okay? VTN driver equal to VTN load equal to 1 volt. KN driver equal to 50 microamp per volt square. KN load equal to 10 microamp per volt square. Okay. The driver MOSFET operates at the key point. So I want to find VI, VO, and IPL, IPD. So VO is here, right? That's the voltage, and it's down to the ground. VI is the voltage here to the ground. IDL here, IDD here, right? First of all, you should know that IDL is the same as IDD, right? If I put a resistor here, that's a different story. Yeah? I did not have anything, so it's open. If it's open, the current here must be the same as current here, right? Okay. So there's no resistor, okay? Second, the low is in saturation, correct? Because the drain is tied to the gate. And the driver is also in saturation 5, because that's one of the conditions, right? Because it operates at the key point, right? Now the key point is on the locus, right? If it's on the locus, it is saturation. Okay. So with that, you are halfway home. See, many of these problems are concept, okay? There are not too many equations, but it is the concept. You have to know the concept. Okay, so this is equal to that, and this equation is KNL BGSN L, right? Low, yes, minus VTN low squared, right? Because that's the equation for situation for the low, and it's equal to Kn driver BGS driver minus VTN driver squared. Sorry, this, there, yes? Okay. Unfortunately, you have more than one unknown, right? This is known, this is known, known, known. That's it. You do not know VGSL, you do not know VGSD. Okay. V sub I should be equal to VGSD. Correct? V sub I to the ground is the same as VGSD. Yes? Okay. And VGSL is equal to VDSL equal to VDD minus V sub L. Right? So this is VDSL, right? VDSL is the same as VGL because these two are connected. And that voltage is this voltage minus V sub L, right? If you do the KVL, that is what you will find. So now I'm going to put this in here. I'm going to put this in here, right? And I'm going to put this in here, right? So I will end now with the following equation. I still have two unknowns, okay? Even though I did the substitution, because now the unknown becomes VI and the VO, right? These are the two unknowns. I still cannot solve it. All right, now, VO equal to VDSD, correct? This is VDSD, yes? So VO the same as VDSD. And that is equal to VDSD saturation, yes? Because this MOSFET is at the T point, so therefore it's the same as the saturation. That is equal to VGSD minus VTND. Okay, good news is that VGSD is according to our earlier no, VGSD. Oh, it's V sub, right? It's V sub. Okay, so therefore I can make a conclusion. V sub equal to V sub minus VTND. Now I'm going to put this in here, and then I would have one equation and one unknown, and the unknown is V sub. Okay, so therefore you can derive the equation for V sub. I'm going to give you the equation right here. It's not very pretty. Lots of parameters. Okay. And of course, everything on the right hand side is known. Yes? So I can plug in the numbers. I will find that V sub I will be equal to 2.2 volts. And then once you know V sub I, you can get V sub O easily, right? So V sub O equal to this minus that. And you get 2.2 minus 1 equal to 1.2 volts. Okay. Later on in the next chapter, we're gonna have to do an example like this, but at that time there will be a small signal attached to the input terminal, and then we have to do the AC analysis to figure out what is the waveform and output. As I told you, this is a very typical circuit. Okay, what time is it? How much time we have left?
30 minutes.
We have 30 minutes.
Yeah, 12:45.
Okay, so with that, this chapter is done. Okay, I assigned you the homework. You should take time to do the homework yourself. So now I'm going to, because we still have 30 minutes, so let me move on to the next chapter. Yes?
Okay, so that means that your IDB is equal to 0.2 milliamps, right? We got from part 1 when we did the printed circuit.
IDD. Okay, if you want to try to find IDD,
We found I IDL earlier, so it's the same, right?
The same.
Usually, okay.
Yeah, it's the same. IDD the same as IDL. Okay, so in this chapter we have learned the DC biasing of the MOSFET circuit. So now we are ready to do the AC analysis. So we are now in chapter 6. So it's the
Chapter
AC operation.
chapter 4, right?
Oh, okay, chapter 4. That's right. Okay. AC operation of band amplifiers. And again, we're going to focus on N channel MOSFET. Okay, so that's the symbol. You have the drain terminal, the source, the gate. Okay, so under the AC analysis, this is lowercase b, lowercase g, lowercase s, right? Okay, and this is the lowercase b, so that's also the same. Okay, so what is the model under the AC condition? Okay. So this VGS, this is open, and this current source is G7 VGS, and this is called Arsenal. So this is I sub B, this is I sub G. According to the model, I sub G is supposed to be 0, right? It's open. Okay, there are two parameters I have to specify. G7 is called transconductance. Okay, and it is I sub B over VGS by definition. And is equal to 2kn VGSQ minus VTN. So that's the formula.
Not square.
No square. And also we know IDQ equal to Kn VGSQ minus VTN to the square, right? That is the drain current under the saturation operation. So therefore, if you combine the two, G7 can also be expressed as 2 times square root of KNIDQ. So you can use this one or this one, okay? It's up to you. Either one, it's okay. R slope is equal to 1 over lambda IDQ. And lambda is called the channel length modulation coefficient. So let me just give you the background briefly about lambda. So when you do the measurements of ID versus VDS, okay? ID versus VDS. You get a family curve, correct? And each one of the curve represent to a specific EG, right? EGS. EGS1, EGS2, EGS2. Always must be larger than VPN, correct? Got it? Yeah. Okay, but this is the ideal case. You can see these are flat, right? But actually, they are not flat. Okay, they have a slope. Okay, so this is the real. And why do we have a slope like that? So the increase of I sub B versus VDS is caused by the decrease in the inversion channel length. So I draw a structure. Okay? So here's the channel length. And then, so when you have saturation, you have this is what we call the inversion channel, inversion layer, right? But you can see that this portion is called the pinch-off region. It does not have electrons. And this region I can call delta L, right? Okay. So delta L actually will go up if VDS goes up. So therefore, the inversion layer length goes down if VDS goes up, right? So if this voltage, this is VDS right here, right? If this voltage goes up, this will become smaller, so that region becomes larger, and this is what we call the channel length modulation. Right? Channel length modulation. So that's why the current actually is not constant in the saturation region. It actually goes up slightly when VDS goes up. And that can be represented by the parameter lambda right here. Okay, so lambda will be equal to 0 if you have ideal case, right? If lambda equals 0, then this becomes infinity, right? And that means you do not have to include R slope. So if lambda is not given, then you can get rid of that. Huh? Okay, so today we have enough time. Let's do one example first. Simple one. Okay, so alright, so it's very simple. So let's say VDD equal to 10 volts, R1 equal to 71K, R2 equal to 29K. VGN equal to 1.5 volts, Kn equal to 0.5 Vn square. R sub B by K lambda. Lambda equal to 0.01 rho minus 1. Alright, so we're going to find voltage gain, current gain. Okay, so the first thing you have to do is to do the DC analysis, right? So this is a VGSQ, right? VGSQ, IDQ, right? Okay. And we can call this VG. So you can see VG is equal to VGSQ, right? And that, according to the voltage divider rule, yes? Okay, so that is equal to 10 times, you have 29K and 29K plus 71K, right? So I get 2.9 volt. VGSQ. Right? Now, IDQ is equal to Kn VGSQ minus VTN to the square. If I assume situation, so we have to verify this later, yeah? So therefore, this is equal to Kn 0.5 times 10 to the minus 3. This is 2.9. VTN is 1.5 square. So therefore, I can find IDQ to be about equal to 1 milliamp. Okay, so now let's go to the output loop. So VDD equal to IDQRD plus VDSQ, right? So therefore, VDSQ equal to VDD minus IDQRD. And all is unknown, right? So VDSQ, what do we try to VDSQ, yes? VDSQ will be equal to 5 volts. Now let's verify this assumption, okay? So VD set equal to VGSQ minus VTN, right? And VGSQ is 2.9, yes? Minus 1.5, so it's 1.4 volt. So VD set is 1.4, which is less than. So you can see that VDSQ is larger than VD set, correct? So therefore, we are in saturation. Yeah? So the assumption was correct. Let's do the AC part. Okay, so it's the same concept as the BJT circuit, okay? C at this time is ideal, so it's a short, okay? So from the left, V sub, right? And then connect it to the gate, correct? But before that, you should have R1 in parallel with R2, yes? Again, under the AC condition, this is connected to the ground, yes? This is ground, so you can flip this, and these two are in parallel, yes? Okay. The source is grounded. Let me make it simple. The drain is connected to R sub B to the ground, yes? And then that is the output terminal. So now you have to put the model into it. GNVGS R sub O. So this is VGS. That's it. So this current, let's call I sub O. This is I sub I. Yes? Okay, first, what is G sub N? We have to calculate G sub N. So G sub N, I couldn't find the value of G sub N. Anyway, you know how to calculate it, right? It's 2 times square root of Kn IDQ, or you can use this equation. What's the equation? Is equal to 2 Kn VGSQ minus VDN. Okay, so either one is fine, but I don't have a value for that. So then R sub O. R sub O is 1 over lambda IDQ, correct? Lambda is given, by the way. Lambda is 0.01. So when lambda is given, then you would have to include R sub O in the model, yes? Okay, so you can do that calculation. Now, D sub O is equal to what? Minus 3 sub N VGS times R sub O is parallel with R sub B, correct? This is the current, and this is the parallel, right? So the current multiplied to that give you the voltage, but I have to put a negative sign, right, because the current goes up. Okay, then what about V sub I? Huh?
I sub I times, that right?
Yeah, V sub I is that current multiplied to that, that's for sure. But you don't know the current. Actually, it's very simple. V sub I is the same as VGS. Yes? Is it? Yeah. VGS. So now you see the key. The key is that you try to derive expression which are a function of what?
BGS.
VGS. Okay? So therefore, A sub E equal to minus G sub M R sub O equal with R sub B over 1. Okay. Well, I do have a number for that. I don't know why. Minus 6.7. So we should go home and try this out. What about A sub I? A sub I, let's say what's I sub I? I sub I is a portion of G and VGS, right? Based on the voltage divided, the current divided the room, yes? Agree? This is the main current, yes? And that's the current divider. Okay. What about I sub I? I sub I is equal to V sub I over R1 in parallel is R2. Correct? And I know that V sub I is VGS. So now you can see I have two equations. Both are a function of VGS. So therefore, A sub I is equal to, this is on top, right? It's on the bottom. So it's minus GM RO plus RB. And then on the bottom, 1 over R1 equals R2. Yes? So I can make it simpler. Okay. So that's the solution of A sub I. Correct? Did I make any mistake? Right now, if I ask you, let's say if V sub I equal to something, let me give you a number. How much time do I have left?
5 minutes.
1 minute?
5.
5. Oh, good, good. Okay. So let's say if I have V sub I equal to 1 sine omega t millivolt. Okay? Then I want to find out what is the voltage waveform at output terminal and I want to find out what is the current waveform passing through R sub P. So basically I want to find if you have a probe at the output, the oscilloscope probe, you can measure the voltage waveform and the current waveform, right? But that is the lab. Here we want to use the analysis to find out, give you a prediction. Okay. The voltage. So the voltage waveform has two components, right? So it has the DC component and it has the AC component. Yes? Okay, so what is the DC component? The DC component, if you look at the circuit, should be the same as what? VDSQ, correct? This voltage to the ground is the same as this voltage, yes? Okay? And we have found VDSQ before. What was it?
5 volt.
5 volt, thank you. 5 volt. Okay, then what about the small signal component? V sub O is always equal to A sub V times V sub I, correct? Now this is the concept. And many people missed that concept last time, right? In the first exam. So, and A sub V was minus 6.7. V sub I is 1 times 10 to the minus 3 sine omega t. So therefore it's a minus 6.7 times 10 to the minus 3 sine omega t, correct? Okay, so therefore, if you build the circuit in the lab and you use a voltage probe, this is what you should expect. Okay, first of all, you have the small signal, right? This is V sub I. Okay, the maximum is what? Is 1 millivolt, right? Okay. At the output terminal, you have a 5 volt, right? 5 volt, that's the DC. And then, alright, that is the waveform you should expect, right? It's a phase difference, huh? Correct? And the maximum should be how much? Yeah, about 6.7 millivolt.
Just 1.7.
Oh yeah, so it's so this value should be 5 plus.
1.6.
Yeah, 0.0067, correct? Yeah. This value right here. And then you know what's this value, right? It's 5 minus that. Okay, what about the current waveform? The current waveform has two current, right? I plus II. Huh? What is the DC current? Huh? So what is the DC current going to RCP? IDQ, right? So we know that. What about here? This is not II, I'm sorry. What am I doing here? We're talking about the output current, right? So this is so IRB, right? Plus IRB, whatever. Okay? Okay. So what is the small signal current? Then if you come here, right? That is I sub O. So this is I sub O, which is equal to I sub I times A sub I, correct? Huh? Okay, what is I sub I? Now I sub I, we know it's V sub I over that, yes? So I sub I is V sub I over R1 in parallel is R2. So therefore, you get a value of I sub I, and then you put here, you get a value of I sub O, and then you plus that, that will be the final waveform. Is it clear? I did not put any numbers, huh? Okay.
Where's A sub O?
A sub I gave you the expression, I did not give you the value.
Okay, I was making sure.